Okay, so I'm gonna get started. I have a bad tendency of bumbling and rambling, and talking too quiet. So if I start doing that and if you have trouble hearing me, just interrupt me and let me know. I won't be offended. I'd rather you hear what I'm saying than me to be like whispering in the corner to myself. So let me know. So welcome everyone. This is the third Blue Food webinar, and I'm going to be covering the results of a project that I've been doing that's been focused on doing a risk assessment of the welfare impacts of climate change on low-trophic aquaculture species. And this work has been funded by York Brooksberget as well as by Blue Food. Before I get going too far, I just wanted to point out that this is part of the Blue Food webinar series. It's the third webinar. There's been two others in the past. One was hosted by the University of Gothenburg. It was about regulatory conditions for Swedish aquaculture. The second one was hosted by RISE and was about the consumption of seafood in Sweden. If you missed these webinars, you can find their recordings on the Blue Food website, which is, I'm pretty sure the recording for this one will be up there as well afterwards. And there's going to be more of these webinars coming next year. I was also asked to point out that Elena Costa, one of Blue Food's PhD students, is going to be defending her thesis on Friday about food neophobia. So if you're interested in that sort of stuff, I'm sure she would love to have more people paying attention to her presentation. So with that, I'll get going. I'll just give a quick outline and try and explain some of the madness behind what I'm doing. This has been the first time I've done a risk assessment, so a lot of this was fairly new to me as well. And I'll be pretty upfront. It's a bit of an imperfect process, but the hope is that it'll be a useful process. So I'm going to try and show you how the process went and what our thought process was behind it, so you could hopefully see why we're trying to do this, why we're trying to get people to start thinking about this. And then hopefully you'll agree with some of the suggestions we came up with. But if not, I want to save time at the end of this where we can have questions and discussion, because that's really one of the main points of this project, is to start getting discussions going. So I'm going to talk for 30 to 35 minutes. If I start going a bit too far over, can you give me a poke also, because I get deer in headlights when I'm presenting.
Yep, sure.
I'll start off by talking 30 to 35 minutes about the project, and then also is going to do a shorter presentation about things from the management perspective a little bit more, and why risk assessments can be useful. And then we're going to try and save 15 minutes at the end for discussion. So I'm going to go over why we should have a risk assessment for climate change, why do it for low-trophic aquaculture species, give you an overview of the project, the methods we used, a broad overview of the risks, and a broad overview of how climate change is affecting those risks, look at some of the drivers of the risks, and then start talking about mitigation and adaptation actions, and more importantly, some of the recommended actions that they have. So to start off, why do a risk assessment of climate change? And unfortunately, things on the mitigation ends of climate change are not looking so great. This is from the recent UN emissions gap report, and what this is showing. Can you see my cursor? So I'm pointing around. Can you see that? Basically, what this is showing is the likelihood of how much warming we'll be having under current policies, the unconditional, nationally determined commitments. I remember what NDC stands for, the conditional ones, as well as if we meet all of our net zero pledges. And it's not looking so great. Even if we do all of our net zero pledges, we're not guaranteed to stay below 2 degrees warming. Not that anything's guaranteed in life, and if we keep going on with current policies, then we're likely to have 3 degrees of warming. So it's not looking great in mitigation terms. I'm not bringing this up to be depressing, bringing this up to motivate us, for this is why we need to start thinking about, we're going to be having climate impacts, so we need to start thinking about what they are and how we're going to respond and deal with them. Which is why it brings us to risk assessments. So risks in ISO are defined as effects of uncertainties on objectives. These could be either positive, so opportunities, or negative, threats. I think when we're talking about climate change, while there are some opportunities, they're going to be mostly outweighed by the threats. But I'll point out some, but I think we need to it'd be nice to take advantage of some of the opportunities, but I think we need to be realistic and realize that there's probably going to be more threats that we have to deal with. And again, the reason why you want to do a risk assessment is so that you can understand what the risks are and prepare for the uncertainty around them through means like coming up with adaptation and mitigation plans. So basically what we want to do is populate this risk matrix so you can get an idea of how many risks are there that are low probability and small consequences, and how many risks are there that are high probability, high consequences, etc. So you can start seeing where we need to start dealing with things. Why risk assessment of low-trophic aquaculture, which low-trophic aquaculture in Sweden mainly means bivalves, so blue mussels and European oysters. We've included Pacific oysters in this risk assessment as well, even though they're invasive and you're allowed to farm them just because they're an interesting species. Technically, there are tunicates and seaweeds that fall under the low-trophic aquaculture thing for Sweden as well. However, because the grant that was funding this from Nordbergsverket was focused on animal welfare, we excluded seaweeds because we couldn't figure out how to define animal welfare for an algae. And while we tried to include tunicates, we didn't end up actually finding any papers that helped us produce risks for tunicates. So this is mostly going to be focused on bivalves. And the reason for doing a risk assessment for low-trophic aquaculture is because there's a lot of conversations and a lot of people suggesting that low-trophic aquaculture is going to be very important for meeting sustainable food development needs and for meeting the sustainable development goals. In conjunction with the low-trophic aquaculture species rely on their environment. They're mostly filter feeders and sessile. They can't move away like a fish could. They're stuck where they are, so they have to deal with the environment that they're in, which is unfortunately why we're starting to see things like this. There was a mass mortality event in the Mediterranean of mussels, which they think is linked to climate change. There's been mass die-offs of marine animals and mussels on the west coast of Canada, which is a little bit of a different situation because that's intertidal there. So it was not just a marine heat wave, there's actual a heat wave as well. So I think they actually died between the tides, but it just gives you an idea. There's been catastrophic collapses of shellfish stocks in Galicia, which they also think is due to climate change. So we're already starting to see some of these impacts, and it's likely that we're going to have impacts in Sweden as well. So we should be thinking about them and trying to prepare. So just to give you an overview of the project, as I said before, the goal is to do a risk assessment of climate change impacts on the welfare of low-trophic aquaculture species. We left out seaweeds. We're trying to do this within a depth-sea worm framework. So we're basically looking at how the environment is changing, so what the state change is being imposed on by climate change, how that impacts the organisms, okay, what the risks to the organism's welfare is, and then how do we respond to that? What types of adaptation and mitigation actions can we do to deal with those risks? And the kind of thrust of the project is to identify and rank the risks so that we can then identify and prioritize actions that we can respond to. So now I'm going to go through the methods and try and walk you through this. It's a simplified version, but hopefully it'll give you an idea. So to start off, we looked at what climate projections there are for Sweden. So we got this from SMHI, specifically SMHI's climate change scenario website. So we used that to get projected changes for things like sea surface temperature, sea surface salinity. And then we did a literature review to look at how we can expect the species to physiologically respond to this. So we're basically trying to put some boxes around the change, and I'll talk about thresholds in a bit and what those boxes mean and some caveats for them. We then used this to develop a list of risks. So this was done by us without other involvement from anyone else yet at this point. So then we took this list of risks and we had an expert workshop as well as a stakeholder workshop. And in that workshop, we asked people to rank these risks based on 5 categories. The first category was the probability of the risk occurring. The second was the welfare impact of the risk. The third was irreversibility. The fourth was duration. And then we had a 5th category that we used for uncertainty because we wanted to try and account for uncertainty around these risks. And I'll talk more about uncertainty in a bit because it's really important when dealing with this. So we got the stakeholders and experts to rank these risks. This was used to populate this risk matrix that I showed you before. After that, we did another shorter literature review where we looked in the literature to see what types of adaptation and mitigation strategies have been proposed by others already. And we took that and we had another workshop where we took our list of adaptation and mitigation strategies that have been suggested in the literature kind of as seed ideas. And we asked the people in that workshop, focusing on the risks that we identified before that were moderate, high, or extremes of the yellow, red, and black boxes, which of these adaptation mitigation strategies do we think would be feasible for each of those risks, and which ones do we think would be feasible to do in Sweden? And from that, we came up with a list of recommended actions. So that's kind of the whole process in a nutshell. So now I'll start giving you an overview of the risks and kind of getting into some of the results. So just to start off, giving a broad overview of risks, there's two main types of risks. You have direct risks, where it's something that would be directly affecting the organism. So in the context of climate change, this would be mainly temperature, salinity, and pH, where they're directly altering metabolic processes / rates of the organisms. I put this slide up here to use as an example. So this is from Eamon et al. 2020, and what this is showing is changes in filtration rate and heart rate of muscles based on temperature. So you have your optimal range where as the temperature goes up, your rates are increasing until you hit the optimal. And then after you go past the optimal, you start having decreases. And one of the physiological thresholds we used was the highest temperature. And this is where your aerobic power budget starts to decrease. So basically you're having worsening conditions at this point. And then the critical temperature. The critical temperature is where anaerobiosis starts. So once you pass the critical temperature, you're kind of in you're in a dilemma because your survival is now time sensitive, and you need to go back below the critical temperature within a certain time frame, or you're going to start to die. So you can actually see on the bottom of the graph here, this is actually mortality. So you're not having really any mortalities. You start to have a little bit of mortalities as you're leaving the optimal range, but then when you start hitting the critical temperature, that's when the mortalities start going up. So these are some of the ways that we were looking at things. So this is an example of a direct risk. So bringing back these boxes I was talking about before, and this is an example of the graphs that we brought to the workshop when we were trying to assess these risks. So this is what we were showing the experts, and we were using this to base our decisions off of. So for example, this is for sea surface temperature and salinity for Minas legilis. So this black box is the optimal conditions. So as long as you have changes within this black box, you're still going to be in the optimal conditions. So if you have temperature increase within this box, you can actually have increases to growth. So that's one of the opportunities. But as soon as you start going outside of this black box and into the yellow box, now you're having effects on your growth. Your growth is decreasing, not increasing. You're having basically more stress to the organism. And then as you get into these red boxes, this is the critical temperature here, then you're having more threat. So you can just see the farther away you are from this black box, the more in peril and the more stress you're putting on the organism. So this is just an example. And you can do this. So this is with temperature and salinity. The same thing can be done with pH. There are caveats to this. These thresholds are not set in stone. You can have local adaptations. So don't treat these numbers as a solid, like, well, you're fine until you're 0.1 degrees from this, and then once you go over it, you're toast. It's not like that. There's lots of variation around this, but it was just something to give us to base our decisions off of, to give us an idea of what was going on. So in addition to direct risk, there's also indirect risk. So an indirect risk will affect something else, which will then affect the organism. So an example of this is risks to food availability. So for example, you can have a temperature increase, which will affect the metabolism of another organism. So in this case, zooplanktons, zooplankton metabolism going up. That increases the grazing rate on phytoplankton. So the zooplankton respond quicker to a bloom, and they control the phytoplankton population more strongly than they did before, and then that can result in shorter blooms, which can then reduce the food availability for bivalves. So this is just an example of an indirect risk. Other examples are things like biofouling. You have higher temperatures, you can have higher growth rates of fouling organisms, you can have higher predation rates of predators. You can also have, for indirect risks, increased resuspension or runoff, so you get more material in the water. That gets to the point where the bivalves start closing up, so you have reduced filtration rates, and you can also have stratification, which causes a bunch of other things. So these are just some examples. I put this picture here from one of Austin's previous projects where they were looking at how fouling changed with depth, but the depth is a proxy for temperature in this case. So you can basically look at these as temperature increases, you will have more fouling occurring. So these are just some examples. But aside from direct and indirect risks, another kind of confusing and difficult part to deal with is you can also have multiple stressors where you have multiple risks happening at the same time. And when this happens, it alters how organisms respond, but not always. You can have different types of interactions for multiple stressors. They can be non-interacting, so it doesn't matter that they're overlapping. They can be synergistic, so it makes things worse for the organism, just adds more stress and more risk. Or they can be antagonistic, where one stress actually mediates some of the problems with another stress. Stressors can be happening at different scales. You can have local stressors that tend to be at higher intensity, and then you can have more like global stressors, which is what climate change would be, that are more background, but they all can add together. And then there's, of course, just to make things even more crazy, is you have different time. The stresses can change over time. So what I'm trying to drive home here is there's a lot of uncertainty with this, so it's hard to predict things. But going through the process can be useful to help us think about some of this stuff. So I'm trying to be very candid and let you know that when we are talking about the risks that we have, there's lots of guesstimation that happens with this. And we're trying to be educated and use our best estimates that we can, but nothing I'm going to present today is like set in stone or certain. So just be aware of that. Take some of the stuff with a grain of salt. Having said that, I will now show you some of the risks. You've been warned. So when we try to get an idea of what this looks like, so this is using blue mussels as an example. I'm not going to go through each and every one of the risks. If you're interested in seeing the full list and going through that, we've produced fact sheets for all the species we covered, and there's a final report. I have links to that in my last slide. So if you want to get more in depth into this, then you're free to go look into those materials or contact me and I'll be happy to talk about it. But for this talk, I'm not going to go into each and every risk. So what you're seeing here is we have our direct risks, we have our temperature-driven risks, we have our salinity-driven risks, and then our pH-driven risks, and then we have these indirect risks. A lot of the indirect risks ended up being about food availability. So we put that kind of in its own section over here, and then there's a bunch of other indirect risks. But in addition to those, we also have the multiple stressors, as I mentioned. And this, while it's also an example of multiple stressors, is one that I especially wanted to point out because there was so many indirect risks towards food availability, is that having lower food availability is going to lower the resilience of these species to other stressors. So it's important to keep in mind. There's risk of coinciding extreme events, not just coinciding stressors, but coinciding extreme events as well. And there is a lot of uncertainty, not just with the models and climate change projections, but also with physiological responses and how we're ranking things and stuff like that. So there's a lot of uncertainty involved with this, and I just want to be very clear with that. Just to point out some of the higher ranked risks for mussels. One was mild winters reducing recruitment. So there's some work that's suggesting that if you have a mild winter where the water temperature remains above 4 degrees, that you tend to have poor recruitment in those years, which is partly driven by changes to predation rates of things like crabs, but also partly because at a higher temperature, the metabolism of the mussels will be a bit higher. However, food availability is really low in the winter because even if it's a bit warmer, it's pretty dark in Sweden in the winter, unfortunately. So you don't get a lot of phytoplankton growing. So there's not a lot of food. So if you have higher metabolic rates and lower food availability, then you end up having more of a problem with your energy budget. What was the other good example? High ranked examples. Another one of the big ones was the pH reductions causing reduced growth rates, and failed recruitment wasn't one of the ones that got ranked pretty high. So this is just giving you an overview of the types of risks we see. When we start getting into the nitty gritty of how many risks and stuff like this, so these are for present day conditions. So we found about 25 common risks for all the species, and then anywhere from 4 to 10 species specific risks. So when I say 25 common risks, those are 25 risks that would apply to all the species together. They were just kind of generic things. For present day conditions, we identified about 20 risks that warrant mitigation/adaptation actions. So those would be, again, the risks that are in the yellow, red, or black categories. And when we look into future predictions, so this is now looking at the year 2100 based on RCP scenario 8.5. The number of risks about roughly doubles. It goes up to about 42 risks that require mitigation or adaptation actions. And we start ending up with some of these extreme risks. I should have noted before that that slide for the blue mussels, that was for RCP 8.5. I always forget to mention that, so I apologize. So this is showing you how much climate change is affecting the risks. We're more or less doubling the amount of risks that we need to be considering. When we start looking at some of the drivers of these risks, temperature was, as you might assume, one of the main drivers. So this is just the proportion of risks that are driven by the different drivers. And the main difference between the present and the future is the number of salinity risks goes quite up, because we didn't really have any salinity risk under present day condition that we ranked as high enough to need mitigation or adaptation actions. So that's just a broad overview of the risks. Again, if you want more details, you can look at the report of the fact sheets or contact me. So now I'll just I'm going to start off with a broad overview of the types of mitigation and adaptation actions, like just broad categories of them, and then I'll get into our recommended actions. So when I'm talking about mitigation and adaptation, I should maybe have mentioned this earlier. Mitigation usually is about preventing a risk from occurring, and adaptation is reducing the effects of that risk. Maybe should have added that earlier. So in the context of climate change, mitigations are things like you reduce greenhouse gas emissions and prevent climate change from happening, so you don't have to deal with any of this stuff, which would be great, but society, unfortunately, is not on board with that plan so far. Another example with this could be land-based aquaculture. So instead of having to deal with the environment that you're growing it in the field, you can just have your land-based aquaculture and control all of your parameters yourself and not have to worry about it. And then in terms of adaptations, these aren't like official categories that were from the literature. This is just kind of my own spin on it from what I've seen. I've broken it into kind of these 4 categories. There's improved awareness, so stuff like having early warning systems and collaborative warning. There's preparedness, so having an emergency plan. This one's less welfare, but I added it anyways, is something like having contingency funds, so if an emergency happens, you have something to help you deal with the actions you need to take. And then because of the way LTA works and you're growing things in the environment, there's not much you can do to control the temperature of seawater if you're in a fjord. So you're quite limited. So a lot of the adaptation strategies that were suggested in the literature tended to be ways to just avoid the problem. So harvesting early, for example, or moving the organisms to another area where you don't have the hazardous conditions. And then the last category that I saw was kind of ways that you could try to increase your resilience. So some stuff like having selectively bred organisms that can cope with higher temperatures, or making sure that your environment has a good species diversity and genetic diversity. So if you have something like a marine heat wave that causes a die-off, you'll have a higher chance that some of the organisms could cope with the higher stresses. So these are like the broad counties. And the way I kind of see it is basically, so this is just my little like trying to make this more understandable, mostly for myself, is you can either dodge the risk entirely via mitigations, or you can try and do things to prepare to make it so that you'll withstand the risk when you actually run into it. So I kind of, the way when I started thinking about this and putting this presentation together, I realized it was kind of a bit like reaction time. You're going to have time where you detect that the risk is actually forming and going to happen. And then you have to have, and then based on how soon you detect that risk coming, it will determine how much time you have to respond to the risk. So this together was basically your reaction time to the risk. And I feel like this is an important thing, and one of the things that I think should be one of the take homes from this is we need to be working on our detection time and our response time so that we will A, know that a risk is coming our way, and then B, be able to do something about it. So yeah, that's my overview of things. Now I'll start getting into our recommended actions, and we came up with 4 recommended actions from our workshop, and they're fairly broad and maybe predictable, but there's also a lot of uncertainty with this thing. And low-trophic aquaculture is not super well developed in Sweden yet, so I feel like the actions we came up with are good places to start, and I'll explain why as I go through them. So the first action was, and this might not surprise anyone, we should do more research to reduce all these uncertainties, because there's a lot of uncertainties involved in this. And I know I probably come off biased as a researcher, being like, oh, we should do more research. And I'm probably preaching to the choir for this crowd for the most part, but it was, and as I said, some of these are a bit generic, but it really is important. So just to give you an idea of how much uncertainty there is, I know I've been hinting at it throughout the slides, but I really want to drive this point home, is you start off, you have uncertainty in models. You have your models and projections. Those models have their own assumptions. For example, the climate scenario they're using, RCP 4.5 or RCP 8.5. Everything I've been showing you today has been for 8.5, because unfortunately that looks like the more realistic scenario based on the emissions gap report that I was talking about earlier. But then, so you have all these models. The models will give you a projection. Then they take what's called an ensemble mean between the models. So you run one model, you get one answer. You run another model, you get another answer. And another model, you get another answer. You average those together, and that's what the ensemble mean is. But there's also, where's my cursor? There's also the max and min to that ensemble mean. And these are projected changes for the average temperature. It has nothing to do with the variation. We tried to get some idea of what that variation would be ourselves by looking at historical data for Gullmarsfjord. So I basically took the historical range around the average for Gullmarsfjord and applied that to SMHI's climate change projections. Oh, I'm going the wrong way. Which is not the best way to do it, but it at least gave us an idea. It has its own assumptions. That's assuming that there's going to be no change in the variability, which there probably will be, but it was better than nothing to give us an idea of how much ranges are on that. So like when you're looking at these graphs, these black dots and line, that's the projections from SMHI. And then these red, green, and blue lines are when I put the variation from Gullmarsfjord on top of that. Another thing about the models is many of them are coarse resolution, so they don't have as much focus on local variation, and that's something that can be missing, which is again why we tried adding the variation from Grumars Fjord, but there's uncertainties associated with that. Then you have uncertainties in the organism response, which is what I mentioned a little bit ago about those thresholds. These are not lines that are set in stone. You can have local adaptations that will affect this. So, and this is all this uncertainty all piles on top of on top of itself. And then you have uncertainty in extreme events. So this little star mark, for example, this was the highest recorded temperature at Gullmarsfjord for I think it was 2008, which I believe was one of the years that it was really hot. So I just put that on here to see how this is. And you can see that this extreme event was well beyond the projections from SMHI. It's also well beyond the variation that I added. So there's a lot of uncertainty to this, which so much uncertainty to the point that when we actually went to rank the risks, there was many risks that we couldn't rank because of that. So you don't have to get too much out of this graph. Don't go cross-eyed looking at this. This is basically just the list of all the risks. And these were the categories that we were ranking the risks on. And the strength of the color is showing how high those values scored. And then they're divided a bit by some of the parameters that they were affecting. But I don't want you to pay too much attention to this. The main thing I want you to get out of this graph is note all the different areas where it's blank, where we don't have anything filled in at all, where it's we didn't feel like we had enough information to rank these risks at all, so we left them blank. And it's not because these risks aren't important. Some of them are actually probably more important than the ones we did rank. But we just we didn't feel comfortable trying to give numbers to these because it was so uncertain. And this is why the first recommendation we have is that we need to be doing more research so we can start understanding these risks that we didn't feel confident dealing with now. So that's the first recommendation. Second recommendation, and this is the broad one as well, is that we should have increased monitoring. I'm going to go through this one stepwise. So we should have increased monitoring. So this would be more observation buoys, more field sampling, however you want to do it. And I also got advice from someone during this process who may or may not be here today, but I won't point out names, that I should try to assign responsibility of these actions to people. So for this one, when it comes to the first one is obviously mostly on researchers and funding organizations to fund the research to do it. It would also be nice if some of the industry members could do their own research, but I think the state of low-trophic aquaculture in Sweden, they probably don't have the funds to do that, so I won't push that responsibility on them. But so for that one, I would say the more research is more on us academics and regulatory agencies that can fund the academics to do that work. So when I say more observation buoys and more monitoring, that's also more responsibility on the researchers as well as government and regulators. However, we should also have more digitalization on farms and have more sensors on our farms so we can see how the conditions are changing and we have data to back up what's going on and we're aware of what's going on. And the purpose, but not only should the farmers be taking their own data and we should be doing more monitoring, we should be doing it in a collaborative way. We should be sharing our data between academics, regulators, and industry. All of this so that we can do things like have better models and forecasts so we can have early warning systems. This graph here, I'm just putting this up as an example because it was something I came across during the literature review and I thought it was a really good example of why this sort of thing is important. So this was from a Copernicus report, and they were actually able to forecast a marine heat wave in the Mediterranean 10 days before the heat wave occurred. So that's huge. That's really important. That's the response time that when I was talking about reaction time before. If we know that something like a marine heat wave is coming and we have time to prepare for it, that allows us to then have our other reactionary responses. So some of those adaptations from before. So before we can even get to the point of doing climate adaptations, we have to be able to know that we have a risk coming our way. So that's why research and monitoring are the first. I'm doing these in order of priority, by the way. I should have mentioned that. So that's why we've ranked research and then monitoring as the first two recommended actions, because that's kind of the first step that we need to before we can really do anything else. So then our third recommendation is something for what you could actually do. And as I said, the options are fairly limited, but the one that came out that seemed the most feasible and the lowest hanging fruit, I guess, would be have some capacity to do depth manipulation to avoid hazardous conditions. So in a lot of the areas where we are doing aquaculture in Sweden, there are a lot of fjords, so we do have a lot of stratification. So when you go below the pycnocline, you can have lower temperatures in the summer months. This is some data from one of ASA's projects. We're shooting here at Christineberg, and you can see the temperature at 25 meters versus the temperature at 3 meters. And in the summer, there's quite a big difference between the temperatures. So, for example, if we had a marine heat wave coming and we knew the marine heat wave was coming, we could lower our organisms below, where my cursor go, below the pycnocline and try and avoid the brunt of the temperature extremes and hope that our organisms will survive. So this is at least a low-hanging fruit and feasible way that we can try and deal with temperature. This can also have both salinity a bit as well. It doesn't cover everything, but it's a place to start. And there are some examples of how this can be done. There's this thing called Shell Elevator, for example, where they've designed an oyster farm that the entire thing can submerge and it can actually move around and stuff like that. I don't think we need something as high-tech in Sweden. Just being able to easily lower and raise cages would be a good place to start, but then that gives us a tool in our toolkit to then respond to changes. And then the final recommendation. Yeah, I'm going too long. Okay, this is the last one.
Or 1.5.
Sorry. More data-driven site selection so we can try and identify climate-resilient areas. So then when we do aquaculture, we're in areas where we have a little bit less risk. And I'll stop there because this is just a summary slide. And again, if you want more details on this stuff, please check out the report and stuff like that. So I'll shut up now and I'll let Asa do her thing. Sorry.
No, thank you. That was perfect. Well done. Okay, let me see if I can share my. How about this? And then maybe try to get that into presentation mode. Maybe. Come on. No. Can you see anything?
We still see your PowerPoint, not presentation mode.
Not presentation mode.
Yeah, we see the like whatever window.
As it is, yeah. Okay. Why does it not?
You press the little thing down near the Zoom scroller button, right?
Yeah, I did, but it won't respond. So I was thinking, maybe I could do another one. Maybe I'll just stop sharing and then share my screen instead. That always seems to work. Which means I won't be able to see you, and you will have to keep track of me, Adrianus.
Okay.
Yeah, all right. So let's go. So I'm just going to try to briefly describe the importance and the relevance of the work that Adrianus has done in terms of management and restoration of native bivalves. And I hope that during this presentation, it will become clear why I want to talk about management of native bivalves and not of aquaculture. For you who don't know me, my name is Åsa Strand. I work as a marine nature conservation manager at the County Administrative Board of Västra Götaland. So I work at Kosterhavet National Park, and managing bivalves is one of the tasks I do. Just a very brief background to the work we do in terms of bivalve management. We all know that mussels and oysters in nature form very important habitats in shallow coastal ecosystems, but we also know that there's really huge challenges for these habitats and ecosystems that they form. There has been a significant decline of oysters in Europe. In this figure, you can see historical records of where oyster beds have been found historically. Nowadays, there's literally no natural flat oyster beds. And we have also done analysis. You can see that this habitat is basically collapsed in terms of the ecosystem services that they provide. We have a similar situation for mussels where, although the picture is more scattered, there's evidence from all across the globe. This is from the US, where there's been a drastic decline in blue mussels from the 70s to the beginning of the 2000s. You can see similar trends. This is the capture production, so harvest of wild blue mussels. It's declined tremendously. And also the production of farmed blue mussels has declined. And all of this jointly indicates that there is a similar situation for blue mussels as there is for flat oysters. In Sweden, we know a bit more about the populations now than before, but not enough. We know that the situation for flat oysters is very likely as in Europe. On the figure here, you can see the harvest of flat oysters over time. And you can see that the harvest used to be quite high. Oysters are actually dredged in Sweden for a long period of time. And we have evidence in historical literature saying that the oysters used to grow in reef structures, in three-dimensional structures, which you almost never find today. And for blue mussels, we also have this anecdotal and also some data evidence showing that there has been a drastic decline of blue mussels on the Swedish west coast. But there are still large knowledge gaps about this. Nevertheless, we try to fill these knowledge gaps. And while I was working as a researcher, partly together with Adrianus, we ran a project called the Bivalve project. So here we started filling these knowledge gaps by exploring where can we find the species, how big are the populations, and answering other questions. So on this figure, for example, you can see modeled distribution of flat oysters. The blue areas are high probability areas of finding oysters, and the red ones are low probability areas. So here it's a first attempt of knowing where are the organisms located. We also made calculations about the population size, and we can see that the majority of the oyster population in Sweden is actually located in the Kostervärderö fjord, where I now work as a manager. If we look at blue mussels, we have a similar figure, but we also can see in terms of population sizes and numbers that very little of the wild blue mussel population is actually located in this area. And most of it is actually located further south, and especially around the islands of Orust and Tjörn, which happens to coincide with the production of blue mussels, the major production area for blue mussels. And I know there's initiatives and efforts going on to actually explore the interaction between the mussel farms and the wild populations. And I'll mention that a bit more later on. We also looked at genetics and oceanographic current modeling to see dispersal barriers, to look at population structures. And this is really important from a management perspective, because if we want to work with enhancing the populations, we need to know that we are enhancing the right thing. We want to work with genetic diversity, especially in a climate change perspective, because if we enhance the wrong genetic type, then that could have really severe consequences in the future. So this figure again shows where you can find similar or the population genetic structure and dispersal barriers for flat oysters. The brown orange areas are barriers, and the blue areas are areas where you have very similar population genetic structure. And the take home from this picture is basically that there's very limited genetic structure for the flat oysters in our part of the coast, which simplifies management. When we look at blue mussels, the picture is a bit different, and we have surprisingly high genetic differentiation between different areas. And if I translate this, simplify the picture a bit and translate this more into a management perspective, this is how we deal with this information. We develop or create management units. So if we want to work with enhancement of wild blue mussels up around the coastal area, then we need to work with also with seed from this area to preserve the genetic diversity within this subpopulation. And similarly with Stigfjord, and I mentioned that before, Orust and Tjörn, that is a very unique population. So this makes things a bit difficult because, as I said before, this is a major production area for blue mussels, but we cannot just transport blue mussels from this area and then relay them up at Koster, for example, because there's different genetic composition of these subpopulations. But because of these declines, and I've already mentioned that a bit, that we are working quite a bit with restoration. In the bivalve project, we actually did the first oyster restoration experiment in Sweden. So we relayed oyster seeds at Koster. And we're also now working quite intensively at the County Administrative Board with mussel restoration. And you can again see the connection to the distribution of the populations and the genetic diversity. Now we have started working with this in the Orust-Tjörn area where we have the major mussel production and where we have access to seed that we can relay to create mussel beds. But now here we come to the important message. What is the interaction between aquaculture and management? Why am I talking about this? Well, of course, active restoration, if we want to use reseeding or broodstock provisioning, this depends on collaboration with the aquaculture sector. And this, of course, means that climate change impacts and mitigation of the impacts on the aquaculture primary production is really important for a number of different reasons. First of all, if the production is impacted by climate change, there may not be sufficient production also for the restoration market. There is actually two different aquaculture markets, one for food production, but one for restoration. And the restoration market is increasing, especially now with a new EU restoration law that is being implemented. Also, we need to know, as Adriana said, are the organisms produced resilient to climate change? Here we see that there is a possible trade-off. One of the solutions that Adriana promoted was adaptation and domestication to produce organisms that are resilient to climate change. This may be a problem for the restoration sector because, as I mentioned before, the genetic diversity and composition of the populations that we enhance is very, very important. Also, Adriana's mentioned fouling. If the fouling impacts the production, this also means that there may be an increase of invasive species and/or pathogens. How do we address this? How does that impact our restoration activities? We cannot support an increased distribution of invasive species. And all of this was active restoration. And of course, passive restoration will also be impacted if there is a reduction in the primary production of low-trophic species because of the ecosystem services that this production provides in terms of water quality, temporary biodiversity enhancement, and potentially seed spillover to enhance the wild populations. So you can see there's plenty of connections between management and aquaculture here. But this is also a two-way interdependence. Aquaculture depends on wild populations too. It's not only the wild populations and management that is dependent on aquaculture. And this, of course, means that increased knowledge of the magnitude of the expected climate change impacts and the impacts on the bivalves will enable adaptive management. And this is something that we try to work with quite a lot in our regular activities. So where there are wild population structures, as I explained for the blue mussels, other local strains which are more resilient to climate change. Of course, then we would want to work with these populations or these strains and maybe include them more in management decisions. This could, of course, also be of relevance to the aquaculture production, because it would be favorable for the aquaculture production to focus on naturally resilient strains. We also discussed a bit before about the climate projections and how that could facilitate site selection, and also the simulations with future impacts of climate change that could help us both allocate aquaculture in more in areas and which are less exposed or less vulnerable to climate change impacts, but also that impacts how we address restoration, because of course we want to work in areas which is less impacted. Can we, for example, identify climate refugia by selecting specific geographical areas or depth to buffer temperature and or salinity changes? And of course, this connection between aquaculture and management, is there aquaculture production located nearby? And are they using local strains? How do we achieve this combination? So to summarize this, this risk assessment that Adrianus has done, you can see how it interacts with the management and with the aquaculture sector. And I really want to highlight how the risk assessment facilitates management. Of course, primarily by providing expanded knowledge and support with how to prioritize. And I know I'm running out of time, so I don't want to go through all of these in details, but it's a lot about helping us to know where, for which species, for which areas can we expect the highest impacts, the most important threats, and what are the thresholds that we need to act upon. And this enables us to prioritize both between measures and also the resources so that we can achieve management which have the greatest impact. And in terms of practical management, I think we mentioned this already. Provide evidence. This risk assessment will provide or help us by providing evidence to change our activities and practices, both by selecting species and strains, prioritizing which species are most vulnerable to climate change, which ones do we need to have high on our priority list, also in terms of site selection and methodologies, of course. But I think something that is really important is also that this kind of work enables improved coordination between aquaculture and restoration, which will benefit both of these two sectors, and both of them will become less vulnerable to climate change impacts. And also, this type of discussions will create a shared problem understanding and a common language between authorities, researchers, and industry, because this is a joint problem. We need to address it together. And in the end, of course, this will lead to more accurate and long-term sustainable management decisions. So I tried to summarize this in a few take-home messages. And the first one is that climate change threatens both bivalve aquaculture and restoration due to this interdependence. But this is also a strength. If you use climate-smart planning, you can actually work to address the problems for both these two activities. And consequently, both aquaculture and restoration must adapt together. And finally, the risk assessment can support this development. And I know this was a bit quick, but I hope that it at least conveyed my thoughts about why this work is important and how it connects to the work we do with nature management. So thank you.
Thanks, Asa. That was great. Sorry, everyone, I kind of failed on saving lots of time for discussion. I talked a bit too much, but we do have a few minutes for questions. And if you guys have any comments, and if needed, I can stay past the hour if people really want to keep talking. So at this point, I'll open it up. So if anyone has any questions, comments, please feel free. Yeah, Christian.
Yeah, thank you very much, Adrianus. Great presentation. I have three points. A question. You show the portfolio of the different risks, and you said that there's a change in the risks, especially because of the salinity. What is the driver for that? Is that more water, more melting water? Is that lower salinity in the future? What is the main driver for that? That would be one question. Let me go through it all. Then I like your this early monitoring system. That would be the ball to you at the academia. There's great works done and implemented systems in Ireland, Scotland. That would be great to have a Nordic interaction of these kind of models. There are already some to just plug and install, but we would need you from the academia to drive that. And then one question to Åsa, there was the picture of the density of the of Ostrea idulis, and you mentioned that there's a concentration of blue mussels together with the farming of blue mussels. Could it be the same with Breivik and our farm? Because I saw very much blue around the Breivik area. Is that coincident, or could you draw some conclusions there as well? Yeah, that's it.
Okay.
All right, Adrianus, do you want to start?
Yeah, I can start. A lot of the salinity-driven risks were low salinity-driven risks, and it was mostly increased precipitation and runoff and stuff like that. That was the main drivers. That's just saying it broadly, but yeah, it was usually low salinity risks. And then the second question about crap, now I'm forgetting it.
The monitoring. I mean, that would be great. It's just an
Yeah.
idea. That would be great. There are already lots of systems in place. It would be great if you could take the ball and adapt and make an adaptation to our waters, and then an integration as well with the others.
I'm going to push back a little bit on that, not because I agree with you. It would be great for us to pick up the ball. We definitely should. But you should also be picking up the ball a little bit and trying to integrate some sensors and stuff onto your farm. Because if you'll remember, I said we need a two-pronged approach to this. So
absolutely,
I'm glad you agree with it. Also, you can do the last one.
Okay, yeah. So I'll just follow up on the last question you discussed. We actually did that already in 2018 and applied for projects to start implementing and building these kind of structures in Sweden, but unfortunately we couldn't get funding to do that. And I think that as things have, perhaps it was a bit premature, but maybe this is the time to start working on this more intensively. So just, we tried, but it's difficult to get funding for that kind of activities. In terms of your question about the seed spillover and your oyster farm in Koster, I don't know. So the map I showed you was the sort of high probability areas for existence of oysters. So what we need to do now is validate these models. And it would be really, really interesting to explore whether we could see a connection between the existence of oyster farms, larval spillover, and then the wild populations, because this is obviously what we hope for. In our terminology, that would be referred to as passive restoration, and something that we're really interested in exploring. But Sara Hornborg, maybe you want to say something about the Attitude project.
No, I wasn't prepared for that.
No, I know. I'm sorry. I just sort of tossed that at you.
So, but starting in April, a 3-year project would run on how to enable restorative aquaculture of bivalves, both mussels and oysters, which is a collaboration between Italy, Spain, the Netherlands, Denmark, and Sweden. So I hope that we will be able to share experiences and learn from each other and make that happen, so that we can identify ways to how to maximize the positive synergies between aquaculture for food and restoration.
Thank you.
Was that what you were after, Åsa?
Yes, yeah, that was exactly what I was after. So it's a really good question, Christian, and we are working on it.
So there were basically a lot of dialogues, I guess, on how to implement this in terms of siting and so on.
Yeah.
Is there any other questions? I realize we're going a little bit over time now, so we should, if there's no other questions, I'll officially end the webinar. But if not, if there are questions, I can stay and keep talking if people want. But yeah, so last call. Any questions or comments? Oh, all right then. Well, thank you so much for coming. I hope this was at least partially useful to some of you, and you can kind of see the point that we were trying to get across with this. And we really just wanted to get this discussion and this ball rolling on this topic. So hopefully there'll be more to come. And if you have any ideas on how to do that, or if you'd like to contribute in some way, feel free to contact me or Ross. I'm sure both of us would be happy to talk to you. But yeah, if not, then I'll end it there. Thank you so much for attending, and this will be put up on the Bluefood website. I don't quite know the timeline for how long that'll take to do, but it will be there. And again, there's links to all the reports in my slides, which I think can also be made available on the Bluefood website. But if you want to get access to them before then, feel free to contact me and I'll hand them over. But yeah, so thank you everyone, and I hope you enjoy the rest of your day. And see you around.
Thank you.
Thank you very
Thank
much.
you. Bye.
Bye.
Yes.